Welcome to Tomorrow Unveiled, where we strap in and explore the technologies redefining the boundary between human and machine.
This week, yeah, we're looking at something pretty fundamental. It seems like the main way we interact with tech, the user interface, it's moving off the screen and directly onto our bodies.
Mm.
The dedicated research team that compiled this information, they found this really powerful convergence happening. You've got high-end fitness tracking, advanced medical device stuff, and cutting-edge augmented reality all starting to blend together.
And that blend, that convergence, it forces us to ask some big questions, doesn't it?
Absolutely.
So our mission today on Tomorrow Unveiled is really to dig into this cutting edge of wearable tech. We want to look specifically at this shift towards sensing intent. Things like neural control, gesture control, and the really deep implications of integrating tech right into our minds and bodies.
We're talking everything from like relatively simple hands-free wristbands all the way up to, well, high-resolution brain implants.
All right. So if you listening thought wearables were just, counting your steps or checking your heart rate, prepare for a bit of a mind shift.
Yeah, the future of how we interact looks like it's going to be incredibly personal. It's driven by data that goes way beyond just physical movement. It's starting to tap into our cognitive state even.
Okay, let's dive in.
Okay.
So let's start with the here and now, the practical side of interacting with our devices.
Yeah.
We're also used to touch screens, voice assistants. They feel pretty standard.
They do, yeah.
But the research suggests they're actually becoming restrictive.
Yeah.
Especially when things need to happen fast. Why is the industry seemingly moving beyond them?
Well, it really boils down to friction, Touch screens need your hands and eyes. Voice assistants need you to speak clearly, and they don't work well in noisy environments or when you need quiet.
Right.
Think about like a surgeon in the OR or someone on a noisy factory floor or even just driving with AR navigation overlaid. If your hands or voice are tied up or the environment's wrong, those interfaces just stop being useful. There's friction.
And getting rid of that friction, that's driving some serious money. The research team pulled up market projections, and the numbers are, frankly, kind of staggering.
They really are. You're looking at a global wearable market starting around, $116 billion back in 2021?
Yeah.
And it's projected to shoot past $265 billion by 2026. That's huge growth.
It's massive. And it's not just about slightly better watches, is it?
No, not at all. That kind of exponential growth, it's fueled by this deep demand, both from consumers and businesses, for devices that are compact, always connected, and crucially require minimal direct intervention.
Okay.
It signals this big strategic shift towards tech being totally seamlessly integrated into life, and you just can't achieve that if you're constantly having to pull out your phone or, yell commands at a speaker.
Right. And the first big leap, the really compelling one happening right now, seems to be this neural input idea, specifically gesture control wearables.
Yes. This is where we start sensing what you intend to do, maybe even before you fully do it.
How does that even work?
The core idea is actually pretty elegant, even though the tech behind it is complex. These wearables use sophisticated AI to basically sense and interpret what you're planning to do just through subtle movements in your fingers and wrist. Tiny, almost invisible movements.
Okay.
They rely on something called electromyography, EMG. It measures the little electrical signals your brain sends to your muscles when it tells them to contract, even micro contractions.
So it's reading the signal to the muscle, not just the muscle moving.
Exactly. It's like a neural input platform that translates those very early muscle signals, that intention, into a digital command. It bypasses the need for a big, obvious physical action.
So we're talking about devices that read the neurological prep for a gesture, not the gesture itself.
You've got it. Precisely. And the fascinating thing is, this isn't science fiction. Our research team found it's already commercially available.
Really?
Yeah, they pointed to early movers like the Mudra Band, that's an accessory for the Apple Watch, and also the Mudra Link, which is designed to work across different platforms.
Hold on, that's interesting. Why haven't the big players, your Apples, your Googles, just rolled out their own versions and dominated this? Usually they jump on this kind of tech.
That's a great question, and it's kind of the interesting competitive picture right now as of 2025. The research shows that, the big tech companies are definitely working on similar EMG wristbands and neural input stuff. Of course they are.
What?
But many of those projects seem to be still stuck in R&D or maybe limited pilot programs, getting the AI calibration right so it can reliably translate those super subtle signals into accurate commands without false positives. That's proving to be a really tough nut to crack.
Oh, okay, so it's harder than it looks.
Much harder. And that delay gives these first companies, the Mudras of the world, a significant head start. They get to define the user experience first, gather real-world data, build that user base.
And the research mentioned that cross-platform ability, like with the Neuralink working on Android, iOS, Windows, Mac. Why is that specifically so important?
Because the future isn't likely to be just one company's walled garden, right? It's going to be about interconnected devices and systems. That versatility means a device like Neuralink can plug into lots of different setups. Crucially, it can integrate with augmented reality glasses now. If you're locked into just, say, the Apple ecosystem, your potential use cases are immediately limited, especially thinking about enterprise or complex AR setups where you need different bits of tech to talk to each other.
That makes sense. But that kind of seamless operation, it doesn't just happen magically. It needs some serious horsepower underneath, right? The sources kept pointing back to the underlying AI infrastructure.
Oh, absolutely. You have to give credit to companies like NVIDIA here. They're providing the processing muscle. Their AI chips, like the Jetson or a Nano, are really key enablers for these intelligent wearables. And we're talking serious computation packed into a tiny space.
The numbers the research team flagged here really jumped out at me. These chips can deliver up to, what, 67 TOPS?
Yeah, 67 TAPS, tera operations per second.
Trillions of calculations every second, on your wrist.
Exactly. And the fact that these little edge devices can crunch numbers like that means they can run pretty hefty AI models, large language models, vision transformers, right there on the device itself.
Without needing the cloud constantly.
Right, which cuts down latency dramatically. It makes that real-time gesture interpretation feel instant, feel reliable, and that's absolutely critical if you're using it to control AR elements or, make quick decisions. Lag just kills the experience.
So processing is one piece. What about staying connected? Qualcomm seems to be pushing boundaries there too with their new Snapdragon platforms, satellite support.
Yeah, the Snapdragon W5 Plus Gen 2 and W5 Gen 2. They're bringing in satellite support using something called NB-NTN, Narrowband Non-Terrestrial Network Technology.
Okay, sounds technical.
Yeah.
What does it mean for me, the wearer?
It means, imagine you're hiking way out in the mountains or working in a really remote area, miles from any cell tower. Normally, if there's an emergency...
Your phone's useless. A brick.
Exactly. But with this tech, your wearable could become your lifeline. It enables two-way emergency messaging straight from your wrist using satellites. No cell signal needed.
Wow. Okay, that's a game changer for safety and just general usefulness in remote places.
Huge. It dramatically expands where these devices are practical, especially for outdoor enthusiasts or people working in industries like mining, forestry, emergency services. Anywhere safety off the grid is a concern.
So if you zoom out and look at the whole picture, you've got these sophisticated neural gesture controls powered by tiny supercomputers with potentially global connectivity. It feels like they're arriving just in time to mesh perfectly with the rise of extended reality, XR, and augmented reality, AR.
They really complement those systems beautifully. Think about wearing AR glasses. Your control methods are often limited, right? Maybe eye tracking, voice commands, or sometimes fiddly hand gestures that need to be seen by the glasses.
Yeah, line of sight issues.
Precisely. But if the system can sense your intent from subtle movements in your wrist using neural input, suddenly your control extends beyond what the glasses can see or what you can physically point at.
Ah, okay.
It offers this truly silent, seamless, hands-off way to interact with digital overlays, navigate menus, select things. It makes the whole AR/XR experience potentially much smoother and more intuitive.
Okay, so gesture control feels like the immediate next step for hands-free. But then there's the next horizon. Brain-computer interfaces, BCIs, that feels like the ultimate integration, doesn't it?
It really does. And the research is clear. This isn't some far-off dream anymore. The pace of development here is just incredible.
How fast are we talking?
We're seeing a rapid shift. We're moving from non-invasive things like those EEG caps you wear on your head that give sort of fuzzy, low-resolution brain activity readings.
Right, seen those in labs.
To higher-resolution implantable systems on chip. SOSACs. Remember, a SOC is basically a whole computer on a single chip. Now imagine that designed to interface directly with your brain.
Wow. And the capability, the amount of data they can handle is also growing.
Exponentially. The research team noted this fascinating trend. The number of channels on these neural interfaces, basically, how many points of neural activity they can record simultaneously, that number has been roughly doubling every 7 years.
Doubling every 7 years.
Yeah. It allows for these massively parallel recordings. You need that huge amount of data, that fine granularity, if you want to achieve really precise control, like for sophisticated tasks.
Okay, let's break down the difference here because it seems crucial. Invasive versus non-invasive BCIs.
Right.
What are the real trade-offs?
Right. So non-invasive, like the EEG caps on the scalp, big advantage.
Yeah.
No surgery. That's huge. And they're pretty good for monitoring sort of higher level brain states. Things like tracking general emotional states, analyzing overall cognitive load, that sort of thing.
But the downside?
The downside is the data quality. Because the sensors are outside the skull, they're picking up signals from large groups of neurons all firing together. And those signals are faint and get distorted passing through bone and skin. So you get low resolution, noisy data.
Okay.
Which means it's just not reliable enough for really precise, multidimensional control, like accurately controlling a robotic arm with multiple joints or interpreting complex visual information.
And that's where the invasive stuff comes in, the Neuralinks, the ECOG arrays.
Exactly. Invasive BCIs, they interface directly with the brain tissue, either sitting on the surface, like ECOG arrays, or penetrating slightly into the cortex, like the electrodes used by Neuralink.
Closer to the source?
Much closer, which means much higher resolution data transmission, and that's absolutely vital for the really ambitious applications. Restoring movement to paralyzed limbs, potentially restoring sight or hearing, advanced prosthetics.
The research pointed to Neuralink's Telepathy device as a prime example, right?
Yes, it's probably the highest profile one. A coin-sized implant recording activity from thousands of electrodes. The goal being to allow users, initially those with severe paralysis, to control computers or smartphones just by thinking.
It's genuinely mind-bending stuff. But sticking a computer chip inside someone's head, the engineering challenges must be immense, especially around heat and power.
Oh, they are formidable. You're putting a device that generates heat inside living biological tissue. There are incredibly strict thermal limits. The research cited a threshold you can't exceed a power density of about 40 milliwatts per square centimeter.
40 milliliters per square centimeter.
Yeah.
Not much headroom.
Not at all. Go over that and you risk damaging the surrounding neurons. Heat is bad for brain cells, but at the same time, the implant needs to wirelessly transmit huge amounts of data out of the skull for processing, and it needs to do it in real time.
And how fast is real time when you're talking about controlling something with your thoughts?
Well, the benchmark the research often uses is basically the brain's own reaction time. Can the system complete the loop, read the intent, process it, execute the command, provide feedback within about 0.18 seconds?
180 milliseconds. Wow.
Yeah. If it's slower than that, it doesn't feel like direct thought control. You perceive a lag, and the whole seamless integration breaks down. So hitting that 0.18 second latency target while staying under the 40 milliW heat limit and doing it all wirelessly through bone, that's basically the defining engineering challenge for invasive BCIs right now.
It's incredible. But beyond just control, these BCIs and other specialized wearables are already making a huge difference in accessibility, aren't they? Restoring functions people thought were gone forever.
Absolutely. The research team highlighted some truly amazing work being done in vision restoration.
Tell me more.
They discussed devices like the Prima retinal implant. This system actually works together with AR glasses. The glasses capture the visual scene, process it, and then transmit that data wirelessly to the implant on the retina.
Directly stimulating the remaining cells.
Exactly. It's helping patients with really severe conditions like dry age-related macular degeneration, AMD, which is a leading cause of blindness. It's allowing some of them to regain functional sight enough to read letters, navigate environments again. It's not perfect vision, but it's restoration.
It's genuinely life-changing. And there are also those AI-powered glasses we're seeing more of, aimed at helping the visually impaired navigate the world more independently.
Yes. We saw that case study, Chriselle Brown, a legally blind woman in D.C., using these AI glasses.
How do they work?
They have cameras and AI on board. She can ask them questions via voice command, like, what's in front of me? And the glasses will give her a detailed audio description, reading street signs, identifying obstacles, describing objects.
Wow.
And crucially, many of these systems can also connect to remote human agents, like through services such as Era. So if the AI gets stuck, you can instantly connect to a sighted person who can see through the glasses camera and provide human interpretation and guidance. It's this powerful blend of AI assistance and human backup.
It really is amazing how quickly this tech is impacting individual lives. It makes you think. And actually, speaking of impact, if you're listening on a podcast service like Apple Podcasts or Spotify right now, we'd be incredibly grateful if you could pause for just a second and leave us a rating and review for Tomorrow Unveiled. It genuinely helps us reach new listeners and allows us to keep exploring these fascinating developments. We'd really appreciate it.
Okay, so we've talked about gesture control. We've talked about direct brain interfaces. Now let's look at something that kind of bridges the gap. Human-computer integration, or HCI, specifically in the context of physical exertion.
Exertion, like exercise.
Yeah, think about technology not just sensing you, but acting as a sort of contextually aware partner while you're doing something physically demanding.
Okay, interesting. The research team dug into this using e-bikes, right, as a kind of test case for how humans and machines negotiate control when the machine is supposed to be helping.
Exactly. They looked at a few systems, but let's focus on two main ones they investigated because they illustrate a really important point about control. One used movement data, the other used physiological data.
Got it. Tell me about the movement one first.
Okay, so this system, the researchers called it AVA. It used gyroscopes on the bike to sense when the rider leaned forward.
Which is what cyclists naturally do when they want to go faster, right? Put in more effort.
Precisely. It's a clear physical cue of intent to accelerate. So when AVA sensed that forward lean, it would synchronously increase the electric motor's assistance.
Ah, so the bike helps more exactly when you signal you want to work harder.
Right. And the immediate effect on the rider, according to the research, was this feeling of empowerment, like a sense of superpower, because their own deliberate body movement was directly, instantly controlling the machine's boost.
Okay, that makes sense. It feels intuitive.
Yeah, the researchers called this a low level of control negotiation. The user has a very clear direct control over the input, the lean, and the output, the motor boost. It feels very satisfying, very integrated.
But the second system, ENO, was different. It used physiological data.
Yes, ENO was more subtle, and the control aspect is more complex. The system used a non-invasive EEG cap, one of those scalp sensor things we talked about, to monitor the rider's brainwaves.
Okay, what was it looking for?
Specifically, it was looking for a brainwave pattern associated with a state called peripheral awareness. This is like being focused, but also relaxed and aware of your surroundings, having a wide field of view. It's linked to activity in the high alpha brainwave range.
So instead of reacting to a physical action like leaning, ENO reacted to a specific mental state.
Exactly. When the ENA system detected the rider was in this desirable state of focused yet aware cruising, it would gradually increase the motor support.
Gradually, not instantly like Ava.
Right, more subtly. And the user's feeling of control here was different. The research team described it as semi-control.
Semi-control, why?
Because you, the rider, could potentially learn to enter that state of peripheral awareness. You could be trained to get there. But you weren't sending a direct, explicit command like leaning forward. The machine was responding to an internal condition it measured, not an external action you dictated.
Okay. That's a fascinating difference. Direct physical command versus the system responding to a monitored internal state.
Exactly. And comparing those two systems, AVA with its direct control and ANA with its semi-control, it really highlights how nuanced our sense of agency becomes when we start integrating technology at this deeper physiological or even neurological level. It forces us to think about what control really means.
Yeah, that shift. Moving from explicitly telling the computer what to do to the computer sensing our physical intent or even monitoring our brainwaves. It really forces us to look again at what we mean by agency and control, doesn't it?
It absolutely does. The research really underscored this. A user's experience how much agency they feel they have. It seems to be directly tied to the degree of control they have or perceive they have over the data the system is using to make decisions.
Like in the e-bike examples.
Exactly. Going from AVA, where your lean directly controls the boost, to ANA, where the boost depends on your measured brain state. That fundamentally changes the negotiation between the human and the machine. Who's really in charge? Or is it shared?
It brings in those philosophical ideas like from Don Ide, the phenomenologist the research mentioned.
Right. Einstein's whole point is that technology isn't just a neutral tool we pick up and put down. Every time we integrate it into our lives, especially these deeply integrated wearables, it actually shapes how we perceive the world, how we experience being in the world.
So when a machine starts responding to our thoughts or our neurostates, the technology isn't just external anymore. It starts to become part of our extended self in a way. And that makes the design of these interfaces, especially things like BCIs, incredibly ethically significant. It's not just engineering, it's shaping human experience.
And the most immediate, maybe the most obvious ethical red flag here is privacy, isn't it? Especially with neural data. It feels like the privacy paradox on steroids.
That's a good way to put it. The core problem is scale and sensitivity. These BCIs, these neurological sensors, they capture vast amounts of brain activity data, often way more than is strictly needed for whatever task they're performing. And this just magnifies all the privacy concerns we already grapple with when it comes to big data. The research suggested we're seeing the same old problems crop up again, just with even more sensitive data.
Absolutely. The team emphasized it raises all the same critical ethical questions. Is consent truly informed when the data is this complex? Who actually owns your brain data? How do we prevent misuse? What about the risk of surveillance or discrimination based on your brain activity patterns?
And the sheer amount of data being generated.
It just proliferates. Copies get stored, analyzed, shared, maybe anonymized, maybe not effectively. It becomes practically impossible for any individual to truly track, let alone control, their complete digital, or in this case, neural footprint.
The example the team used about cell phone location data really hammered this home for me. How even anonymized data isn't always anonymous.
Yeah, that was a stark reminder. They showed how researchers could often re-identify individuals from supposedly anonymized location data sets just by looking at patterns, like where a phone consistently ends up at night, probably the person's home address.
Right.
So if relatively simple location data can be de-anonymized like that, you have to ask, what are the risks when we're talking about huge streams of high-resolution data that reflect not just where you are, but potentially your intentions, your emotions, your cognitive state? The potential for misuse is, well, it's significant.
And then layered on top of the collection issue is what happens when we feed this data into AI systems for analysis. That brings us to algorithmic bias.
Yes, and this is especially worrying for wearables used in health contexts.
How does the bias creep in? It's not like the AI is intentionally prejudiced, is it?
No, not usually. It's more structural. AI systems learn patterns from the data they're trained on. That's all they do. But if the training data itself reflects existing societal biases or imbalances...
The AI learns those biases too.
Exactly. It learns them and then applies them, often amplifying them in the process because it does so consistently and at scale.
The healthcare example the research team discussed really illustrated this danger, didn't it?
It did. They described a hypothetical scenario. Imagine a national health system uses an AI tool, maybe linked to data from wearable health monitors, to help prioritize patients for specialist referrals.
Okay, that's efficient.
Maybe. But what if that AI was trained primarily on historical patient data from, say, large, well-funded urban hospitals?
So it wouldn't have much data on rural patients or maybe certain minority groups who are underserved by those hospitals.
Precisely. The training data has a built-in demographic skew. So the resulting algorithm, simply by reflecting the patterns in its training data, might systematically deprioritize those underrepresented groups for referrals, even if their medical need is just as high.
Because they don't fit the typical patient profile the AI learned.
Right. And just like that, bias embedded in a diagnostic wearable or a referral algorithm could actually worsen existing health disparities. It highlights how careful we have to be about assuming these tools are objective just because they use data. The data itself can be biased.
It's a serious reminder to look under the hood of these systems. And speaking of looking critically, if you're finding this discussion insightful and you're watching on YouTube, please take a moment to like this video, subscribe to Tomorrow Unveiled, maybe hit that new hype button apparently that helps us reach more viewers, and definitely turn on notifications so you don't miss our future explorations.
Okay, so we've talked data bias, privacy. Let's shift from the potential unseen harms in algorithms to the very visible issue of corporate accountability and ethics, especially around the hardware itself.
Right, because these wearables are physical devices we buy and rely on. The research brought up the battery date case involving Apple as a key example here.
Yes, it's a classic, unfortunately. It culminated in massive settlements, about $113 million to U.S. states, plus up to $500 million back to consumers.
Remind us what the core issue was.
Essentially, Apple was found to be throttling or slowing down the performance of older iPhone models through software updates. Initially, the justification was framed around managing aging batteries to prevent unexpected shutdowns.
Okay, which sounds plausible on the surface.
It does, but the lack of transparency was crucial. Users weren't clearly told this was happening or why their phones suddenly felt slower. And the practical effect for many was that their phone became frustratingly sluggish.
leading them to believe they needed to buy a new one to get decent performance back, which, of course, fueled lawsuits alleging consumer fraud and planned obsolescence.
Exactly. And this case perfectly highlights that fundamental conflict between stockholder interests, maximizing sales, protecting trade secrets about performance management, and stakeholder interests.
Meaning your customers.
The customers, yes, who expect transparency, expect their expensive device to last a reasonable time, but also broader stakeholders like environmental groups concerned about the e-waste generated when devices are prematurely discarded.
The research even touched on the ethical compromises this forces on employees inside the company.
That was a really interesting angle. It's not just executives making calculated decisions. Think about the software engineer who's tasked with writing code specifically designed to slow down a perfectly functional device. Does that align with their professional ethics?
Probably not.
Or the customer service rep who has to follow a script pushing upgrades rather than explaining the real technical reason for the slowdown. Or the salesperson who knows the product is, in a sense, designed to degrade within a few years.
It creates this internal moral friction.
It really does. The Batterygate example serves as a potent reminder that ethical considerations need to permeate the entire tech development and business process. Failures often happen when transparency takes a backseat to profit, even if the actions are arguably legal. The impact on trust and user well-being can be profound. #outro.
So wrapping up our journey today, it seems clear that wearable tech is moving far beyond just tracking steps. We're really entering an era of deep neural and physiological integration.
Yeah, the potential is incredible. We're seeing pathways to restore lost functions, to augment human capabilities in ways that seem like science fiction just a short while ago, from AI glasses guiding the visually impaired to systems that literally merge our brain state with machines.
But as we've explored, that amazing progress comes hand in hand with some serious and growing ethical challenges.
Definitely. The sheer volume of sensitive neural data, the risk of algorithmic bias deepening societal divides, that constant tension between corporate imperatives and user rights, these are huge issues we need to keep wrestling with.
And we really want to know what you think. Whether you're joining us on YouTube or listening via your favorite podcast app, please drop a comment. Let us know your thoughts on wearable tech, on human-computer integration. How do you personally weigh the potential benefits against the privacy concerns? Where do you draw the line?
It makes you think about that ethical center, like the one proposed by philosophers such as Martha Nussbaum, focusing on human capabilities, on human flourishing.
Right. If the ultimate goal of technology is to enhance our potential, what does that mean for technologies that might create dependency or subtly chip away at our agency, our sense of control?
It's a fascinating question. If we reach a point where automation and AI handle all our basic needs, like Maslow's hierarchy suggests, and wearables let us augment our skills, even our identity, could the next big struggle be less about physical survival or control and more about preserving our sense of self, our mental autonomy, in the face of ever more integrated technology?
A provocative thought to end on. We'll continue to track that complex, evolving relationship between technology and what it means to be human next time here on Tomorrow Unveiled.